So we're going to build a piece of electronics from the ground up. But, forget the soldering iron and the circuit boards. We're doing this entirely inside a computer, a place where we can build, test, and even break our creation before it ever becomes a physical object. Let's dive in.
And that right there is the fundamental challenge for modern engineers. I mean, the components that power our entire world, from our phones to our cars, are microscopic. We're talking about parts that are literally thousands of times thinner than a human hair. So how on earth do you even begin to work with something like that?
Well, the answer is simulation. You create a perfect digital twin in a virtual environment, what we call a digital sandbox, where you can literally play with the laws of physics. With just a few clicks, you can define its size, its material, its properties. It's the ultimate modern laboratory.
So here's our game plan. We'll start in that digital sandbox, build ourselves a virtual diode, and see how it behaves when it's just sitting there. Then, we'll flip the switch, check its signature curve to see if it works, and finally, explore why this whole process is such a game changer.
All right, let's get our hands dirty. Virtually, of course. First up, creating our virtual diode. Think of this as the recipe for a microscopic component.
And you know what? The recipe is surprisingly simple. It really just has 3 key steps. First, we have to define its shape and size. Second, we choose what it's made of. And third, and this is the magic step, we give that material an electrical personality.
For steps 1 and 2, we're going to keep things super simple. Our geometry is just a tiny little block, only 1 micrometer long. And the material we're going to use is the foundation of the modern world, pure silicon. Right now, it's just a boring, neutral little thing.
Now for step 3, giving our silicon some personality. This is done through a process called doping. And yeah, I know, it sounds a little weird, but it's really just about intentionally adding tiny, calculated impurities into the silicon. That's the key. These impurities completely change how it conducts electricity.
So in our simulation, we basically split our tiny silicon block in half. On one side, we apply what's called p-type doping, which creates an abundance of positive charge carriers. Just think of these as empty parking spots for electrons. We call them holes. On the other side, we use n-type doping, and that creates an excess of free-floating negative electrons. So now, our once uniform block of silicon has 2 very, very different halves.
Okay, our virtual diode is officially assembled. So now let's see what happens when it's just at rest. It's time to run the simulation and watch the physics come to life.
The second we start the simulation, physics just takes over. The extra electrons from that n side naturally rush over to fill the empty holes on the p side. This creates a really thin barrier right at the junction where all the free charges have basically canceled each other out. This barrier is called the depletion region. It's kind of like an electrical no man's land.
And this is where you really see the power of simulation. The computer spits out a graph that looks like it's straight out of a physics textbook. We see a ton of holes on the left, a ton of electrons on the right, and then boom, right in the middle, at that junction, the concentration of both just plummets to nearly 0. Our virtual depletion region? It's there. It's real.
Okay, so our diode exists, it has its barrier, but the big question is, does it actually work? Time to flip the switch and put our virtual creation to the test.
Here's how we test it in the simulation. First, we add a metal contact to the positive P side. Then we add a ground to the negative N side. And then we just tell the software to slowly apply a positive voltage, ramping it up from 0 all the way to 1.5 volts.
And this brings us to the signature curve, this single graph. This is the moment of truth. It's going to tell us everything we need to know about our diode's performance. For a standard silicon diode, there's a magic number, about 0.7 volts. This is the tipping point. It's the exact amount of push needed to overcome that internal barrier we just saw. And what do you know? Our simulation nails it perfectly. Below that threshold voltage, almost no current can get through. The gate is basically shut. But as soon as we push past that 0.7 volt mark, the barrier shrinks, the gate swings wide open, and current starts to flow freely. This confirms our little component is working exactly as a diode should. It's a one-way valve for electricity.
Just look at this table. It breaks it down so clearly. At 0.1 volts, nothing. At 0.6 volts, still basically nothing. But once we hit 0.8 volts, the current suddenly kicks in. And by the time we get to 1.5 volts, it's flowing without any problem. Our simulation has successfully recreated the fundamental behavior of a real diode.
Okay, so we've built this thing in a computer. It works. But let's pull back for a second. Why go through all this trouble? What's the big picture here, moving from the digital sandbox to the real world?
Well, the reasons are huge. Building physical microchips is incredibly expensive and slow. Simulation lets engineers build and break thousands of virtual prototypes, saving millions of dollars. It's how they can test wild new ideas and perfect their designs without ever stepping foot in a factory. And the same basic principles we just used for this one diode, they're used to design the CPUs, the LEDs, and the solar cells that are powering our future.
And this really brings us to the final and most exciting question. If we can perfectly model and invent the building blocks of today's technology inside a computer, what does that mean for tomorrow? What revolutionary new devices are being built, tested, and perfected right now entirely